We might leave it there. I do note that there was another question and I've got lots. So maybe we can talk about them over dinner tomorrow night. So our next speaker today is Alex Fraser. Sorry, and Alex is going to be talking to us about altimetric observation of wave attenuation through the Antarctic marginal ice zone using IceSat-2.
Yeah, I'm not talking about fast ice, Rob. It's a first, but I can't resist. So I have one thing to say about fast ice. Yeah, can you just get up my browser? Just share the whole thing if you like. Yeah. Thank you. Just following on from Rob's great talk, fast ice has plummeted in 2022, and this is a result from our fast ice review paper that we just submitted to Reviews of Geophysics. There's a preprint online if you like as well. Just following on from your comment, Ken, Pat knows about some measurements of the physical properties of consolidated platelets, right? Actually pretty strong. Consolidated platelets do have a lot of mechanical strength, right? Yeah. So, yeah, the friable stuff's pretty weak, sure, but when it consolidates, I think there is some strength there. Sorry, I'm diverging into lots of different things. Great. Okay, so today I'm here to talk about some fantastic work done by Jill Brower, who's the first author on this this work here. So she was an honours student that came to UTAS in the year 2000 with a biological background and said she really wanted to branch out into something a little more physical. And so we gave her this project. The idea was to use laser altimetry to measure the wave penetration and attenuation within the Antarctic marginal ice zone. So here's a picture of Jill labeling a bottle, but she's much more versatile than just labeling bottles, and she did a fantastic job. She actually won the prize at IMAS for the best honours at cohort. And Pat Wongpan in the audience and Rob are also co-authors on this work too. So I also just wanted to shout out to Damien Murphy, my Fourier sensei. I think everyone should have a Fourier sensei. This guy can tell you the Fourier transform of any function just like that. It's fantastic. Maybe you don't need one, Ken. Maybe you are the Fourier sensei in the room. So this is all kind of motivated by the fact that, for example, with Alison Cahoot's great paper, a figure out of that here showing that flow breakage can happen an awful long way from the ice edge. So we know that the waves must penetrate a long way in there, right? We know from buoys that waves can penetrate a long way into the marginal ice zone, but buoys just really give a couple of points. And the other motivation of this is that the definition of the marginal ice zone, this magical 15 to 80%, probably doesn't really relate to the marginal ice zone, at least in the Antarctica. So I call it a definition of convenience. And I know there's been a lot of work done on this recently, that sea ice concentration doesn't necessarily have a whole lot to do with any reasonable definition of what we would call the marginal ice zone. So we know from work that Rob done in 2008 that we get these compaction events, and this is where northerly winds blow the ice up against the coast, and you can see that in the Amundsen Sea here. And you can't tell me that a wind that's blowing sea ice from the north to the south with that ginormous fetch of the Southern Ocean there doesn't also have a whole lot of waves, really big significant wave height to the north of that ice, and waves penetrating into the sea ice. But, you know, under the traditional sea ice concentration definition of marginal ice zone, this would not be a marginal ice zone. So there's a big disconnect going on there. And this is a figure from Alberto's Nature Communications paper that was published this year. This is the stereo camera system that they've installed on the South African ship, and we're getting something on the Australian ship later this year as well, a stereo camera system showing, again, 100% ice concentration, but obvious waves. So there's a disconnect between this definition of convenience and what actually should be the marginal ice zone. So we need better satellite observations of the true marginal ice zone, and altimetry holds the key to this. So can we measure the penetration of waves in sea ice from space? Sure, people have been doing it since 1984, and this Rapley paper has hardly even been cited. A Nature paper in 1984 using radar altimetry to measure the marginal ice zone. And I'll just show you a figure from this because it's really cool. So this hatching in the Southern Ocean is large significant wave height from the same instrument, from a radar altimeter. And this black area fringing Antarctica is what they determined as the marginal ice zone. So basically, they look at satellite transects going from north to south, from the open ocean, past the ice edge and into the pack ice, and they see a decrease in the significant wave height, and that's what they call the marginal ice zone. So this is not resolving the waves, but it's a radar altimeter, like a coarse resolution way of looking at attenuation. The interesting thing to note is you get a deep marginal ice zone in regions where you have a large significant wave height to the north. So there's something going on here. So these are 3-day maps of what is probably a really good marginal ice zone. And why haven't we been doing this? It's a bit crazy. We'll come back to this a bit later. Now I want to talk about ICESat-2. So ICESat-2 is a laser altimeter. So we have a very focused beam of light, and we're measuring photons coming back from that. The footprint of this is really fine. So we're talking about a 17-meter footprint, which is easily able to resolve the kind of periods and wavelengths we're looking for. So when we talk about long wavelength penetration, we're talking about, kilometer scale wavelengths. So we can most definitely resolve that directly with ICESat-2, but clouds are a big problem. What I'm showing you here is one particular track, and this happens to be the best ever cloud-free scene showing wave penetration from Antarctica. So this track is going from north, from the ice edge, south to the continent. So we've got distance from the ice edge in kilometers on the x-axis from 0 up to more than 1,000. It's quite a long track. And the y-axis is height in meters. Now we're using the ATL-07 product, which removes things like geoid, tides, really long period things, but it doesn't remove waves. So we can use this to determine the marginal ice zone, or at least the wave penetration. So you can see in this particular case, we've got an amplitude of the wave of about 2 meters, and there's obvious attenuation in this triangle. And so this is what we call the apparent mist. And we're going to use some techniques to do some statistics on this. I'll just bring attention to Chris Horvat's 2020 paper. This also used the same products from the same instrument. He was just looking at where we get negative heights. The problem with that approach is if you've got thick ice, which is also under the influence of waves, and if the ice thickness is of the same amplitude of the wave height, then you're not going to get negatives. So this is a little more sensitive, our approach here. So if we plot, again, distance from the ice edge on the x-axis and wavelength on the y-axis, and the color scale is the spectral amplitude, we get this characteristic triangle shape, which is basically showing us wave attenuation. Now, they don't all look this good. As I said, this is the best ever track that's ever existed in the history of humanity. And we'll come to the problems when we get clouds in a little bit too. Here's a spectrograph of it. Now, the colors are now in distance from the ice edge. So red is very close to the ice edge. Blue is at about the limit of the wave penetration. And you can see this region of preferential attenuation of shorter wavelengths here, as you would expect. The longer ones penetrate more. So the idea is we use the height data from ATL-07 from the ICESat-2 instrument. We calculate significant wave height from that. We plot that as a function of distance from the ice edge. And lo and behold, we get this beautiful picture of the attenuation. And we can see in this particular case, we're getting waves penetrating into about 179 kilometers. you want to use a mic? Oh, sorry. Let me run. You've done a lot of running. Just keep it. I know you need.
So how many dots are on that picture?
Yeah, so let me get this right. This is resampled to about, it's a 6 kilometer window, and we've got one, we're sliding it by 1 kilometer.
Okay, yeah.
So there's a lot of measurements in each of these dots.
But the other picture didn't have that sliding. The previous one, was
These are
without it.
just the 6 kilometer segments.
Yeah.
Yep, that's right. Yep. So now let's compare that to what we get from the traditional definition. So we're saying about 179 kilometers. Actually, it changes to 181 here for very complicated reasons. I'll talk to anyone about it after. Anyway, we're getting about 180 kilometers, whereas the along track sea ice concentration, this is the 15 to 80%, would tell us that this MIS is only 30 kilometers wide. So we're getting a huge mismatch in MIS widths using our technique versus the traditional technique. So missing from this presentation because of time constraints is exactly how we did all the Fourier techniques. But I will just introduce this one little problem that we had. Here's a different track on a different day. And you can see, if I can stop shaking, there, little gaps there. This is what happens when we get clouds. This is a laser altimeter, can't see through the clouds, so we get a lot of gaps. And this might seem like a minor thing, but whenever you get a few clouds, it really messes with the Fourier techniques. So because of Parsifal's identity, if you get gaps and you don't really account for them properly, then you can mess with your spectral power. So there's a way around this. You can make this WSS correction function for the spectrum, and you can implement that, and you can actually deal with these cloud gaps fairly well. In the end, we actually chose a different technique. So Fourier Sensei implemented this spatial domain filtering. It's a little simpler. So what you do is you make it's basically a sinc function or a sin x on x function truncated at about 3 wavelengths. And you convolve this in the spatial domain. And it removes a whole lot of problems. You don't need to do this complex accounting for the gaps. In the end, we implemented both techniques and they both gave almost exactly the same answers. But yeah, clouds are a big problem. We validated this technique using some buoys. So these were the NIWA buoys deployed from the Shiraz. Pat actually deployed these buoys. They measured wave spectra, and what we found is that within about 300 kilometers, we got a significant correlation between the significant wave height reported by the buoys and reported by our satellite technique. So that was encouraging, but we still underestimate the wave reported by the buoys by about a factor of 2. It's not really surprising because these techniques are so completely different. Now to the results. So now this technique involved quite a lot of manual steps, and I'll talk about that a little bit later as well. In the end, we were only able to do it for 4 months within the constraints of a 8 months honours project. Anyway, for those 4 months, what we found consistently was that the MIS width from our technique was about 7 times wider on average than the simple 15 to 80% sea ice concentration. And the seasonality agrees quite well with the seasonality of wave height in the Southern Ocean. So this is kind of an encouraging result. But we do possibly have a selection bias here because, as I said, there's a manual filtering step. We need to see obvious attenuation with this technique before we can characterize it. And the obvious attenuation obviously comes when we have really big waves. So we think we might be selecting for these really strong wave cases rather than these kind of weak wave cases where it's harder to see the attenuation. So there's some scope to improve this technique to make it more representative. Anyway, Noah, in his fantastic work that he presented at the customer workshop last week, has run SICE in a, gee, I didn't expect to have to explain your project, no. SICE version 6 with the joint flow size thickness distribution forced by WaveWatch 3 hindcasts propagated into the sea ice. How am I doing? So NOAA's, and then clustering the results based on flow size and thickness and a few other things. Okay, NOAA came up with this blue line here, MIS width using all of those techniques, and then compared them to Jill's work, which was published earlier this year, and found a really good correspondence between Jill's numbers and your MIS width for most of the year. We got a lot of problems in December because we got waves coming from directions that we can't really account for using a single satellite that goes basically north to south. So we have less confidence in our December numbers than the other months, basically. The other thing that's interesting is, so NOAA has used the exponential model in our attenuation here, and we actually found slightly lower residuals when we used linear attenuation. And again, this is coming back to your great talk this morning. I think that because we are selecting these obviously high energy events, we've got a lot of long period waves going a long way. And as your work showed, these tend to have a lower N, which is closer to a linear attenuation, potentially what's happening there. So this is the wrap up here. This technique has a lot of potential, but we need to automate it and we need to make it able to do its great things even when there's small waves. And we can't account for wave direction with this, right? We've basically just got a slice along Antarctica and we have no knowledge of the wave direction. But, you know, there's this great thing, SWAT, that's being launched in 3 weeks, 5 days and 5 hours. And this is a synthetic aperture altimeter, and it's able to resolve heights, both along track and across track. So we'll be able to see directions and get complete wave spectra out of this in the MIS. It's going to be really good. And this is actually prime time. So if anyone wants to Zoom me and we can watch the launch together, that'd be great. But we need more validation data as well. Now, coming back to this great Rapley technique, I've actually got some small funding to reinvigorate this and kind of maybe resurrect this technique using modern radar altimeters. So thanks to the Antarctic Science Foundation, I'm able to employ Wang, my great PhD student who's just about to graduate, in this project to try and resurrect that technique. So wouldn't it be great if we could get great altimetric maps of the MIS every 3 days back to 1980 something? Yeah, and why has nobody done this? Chris Horvat's the one who told me about this, so we'll get him involved in this as well. Now, I'll just finally end on an ad. So for the last couple of years, I've been the deputy head of CIS at IACS, the International Association of Cryospheric Science. Did I get that right? Yes, at the IUGG. And one thing that they're really interested in is reinvigorating the CIS arm of IACS. And one of the things that we're proposing within that is a working group on Antarctic marginal ice zone. So at the moment, we kind of have a dream, but we don't really have any solid plans. I'm pretty new to this field. I'm not going to volunteer to chair this working group, but you know, somebody in this room definitely could. So we're really interested in feedback at this stage. So we've got a good scope, but we don't really have any scientific goals per se, and they're really important in the working group for IACS. So this ad just went up this morning actually to all IACS members in the November newsletter. Please get in contact with Takanobu and myself if you're interested in becoming a part of a working group that would kind of bring the community together. The overhead shouldn't be too much. There's a little bit of seed funding available for conferences and that kind of thing. Felicity is the chair of a joint commission within IACS and IAPSO as well. So it's a good thing, huh? Yeah. Great. Thank you very much. Especially great thanks to Jill, who did a great talk. I mean, a great work. Thank you. Cheers.
Thanks very much for that, Alex. I love your Nathan Pyle cartoon as well. Does anyone have any questions in the room or online?
Hey Alex, great stuff. Do you see any evidence of different rate of attenuation close to the ice edge that Agnieszka brought up earlier and others have discussed? Well, the thing that you just went past there, I kind of wanted to buy into very high attenuation at the edge. It's vertical, basically.
Oh, this right here.
Yeah.
Yeah,
Well,
interesting. So I hadn't even looked at that, but that's super interesting now that you bring it up. I wonder how robust that is.
Yeah, well, I was thinking more about, I mean, okay, I'm guessing that's not physical, but please prove me wrong. But then you were talking about the relationship with the concentration, maybe slightly indirectly, but there might be something in that. So this is how the attenuation rate changes as the concentration increases.
This is also corrected distance from the ice edge. So anything that's not consolidated gets mathematically consolidated into the first kilometer or so. Right, maybe that's what's happening. Yeah.
Okay. All right. Thanks for pointing that out. And the other one, just a comment. Thanks for showing Noah's result. I saw that for the first time on Monday last week. It's already been presented at 3 conferences. So I hope it's right.
I am interested in your reluctance to call the marginal ice zone those events when the waves are large. Why not? When, after all, isn't it an integrated effect over time? And it seems to me that the concentration is affected, the flows are affected for more than just the event. So
yes, we had a reviewer comment like this too. In the end, we ended up calling this the wave-affected marginal ice zone or something. But the problem we have is, so we get 14 tracks a day, but 13 and a half of them are cloudy. So we're really only picking out, we're still only doing snapshots here, really. So even this, even though it's deeper, may not be representative of what's really the MIS. But, when radar altimetry technique is resurrected, we won't have the cloud problem. I think that would be a much more representative picture of the MIS. Yeah. It's tricky. Those damn clouds.
So we've got time for one more question, and Roland just asks all questioners to perhaps say their names and then give their questions.
Yeah, good idea. It's Mike Malin here. Thanks, Alex. I'm just curious, when you go back, the thing that I'd like to do with what one thing we can do is just wait till they launch this new satellite and then it'll solve all our problems. I think that's a great idea, and just have a break for a couple of years from science. I've got some other stuff I need to do. But no, the one with the spectra on it. Yeah, the next one. Yeah. No, go forward one, sorry. Yeah.
That one?
Yeah. I sort of feel like somehow you could get the attenuation as a function of frequency out of that. I mean, you've got a whole lot of dots that Agnieszka could join, haven't you? Like you've got all of those lines of dots, and then she could put a curve through them, and you could see. Yeah. I mean, it gets a bit, it's noisy, yeah, or you could see if it fits that linear or it fits these other powers. I almost think that I'm not sure how, maybe this is too noisy, but it'd certainly be worth looking at from the way she looked at it.
One problem is we probably aren't aligned with the wave crests and troughs. So we're probably elongating all the wavelengths just because of the mismatch. Without knowledge of the wave direction, that's tough to account for. I know Chris Horvat was using the 3 strong beams, which are spaced about 5 kilometers apart, to try and get some measure of the wave direction as well. So, yeah.
Roland, I see that you've raised your hand, but we're going to have to move on to our last speaker of the session. So perhaps you could pop it in the chat and I'll get Alex to monitor the chat too. Please join me again in thanking Alex.